All right, let's get started here. The grader has posted feedback for the first assignment that he's graded of yours, and he's going the extra mile on that. When I've graded stuff in MU Online, I just put comments like in the little text box by the score. That's the lazy way. But I guess my grader's not lazy. What he's doing is he's going in and there's annotations that he can leave right on your PDF. So when you look at the PDF, there's comments, and you can click on that comment, and it'll pop up. And so he's kind of trying to give you more context-specific feedback on like where your mistake is and what the answer should be. So I'm grateful to him for doing that. I hope that it's useful to you. What my suggestion is when you do the homework, close the loop, as they say. You know, like if you've made a mistake, go in and diagnose what was the error in thought. Go through, fix it, so that you have a clean solution, like the way it's supposed to be solved. So make use of the grader's feedback, and you'll be that much more prepared when the exam day rolls around. All right, the next announcement is this assignment, which is due a week from today. It's a long one. There's lots of problems there. And so my suggestion is to get an early start on that, because it's not going to be easier by procrastinating. It'll just make it harder. If you get an early start on the assignment, then that'll give you more time to ask me questions and give me more time to respond. And we'll go over some key ideas in class on Thursday to help you into some of these more complicated problems. But I'd definitely suggest that you get an early start on that assignment. Finally, so I already announced in our previous class that I put a sample exam on MU Online. I've also posted the equation sheet that you're going to have available to you during the tests. So you look at that, start familiarizing yourself with what I'm providing, the format it's in. The variable definitions aren't provided, just the equations. And so kind of you're going to have to meet me halfway on that formula sheet and know how to use the equations and which numbers goes into which variable. So any questions on the announcements? All right. What we're going to be talking about today is some applications of the hydrostatic equation. Last time in class we solved the hydrostatic equation several different times in various ways. We're going to look at how the hydrostatic equation is applied today. So just to refresh our memory, and as a review, let's use the hydrostatic equation both ways, both in terms of absolute elevation measurements. On the left-hand side of this equation, what we're saying in this form of the hydrostatic equation is, let's assume that we're measuring elevations according to some datum. So we'll use the bottom of the tank as our datum, where this is 0 elevation. And so then what that means is that location 2 is at an elevation of 15 meters. Location 1 is at an elevation of 50 meters. So let's find out what is the pressure here at location 2 according to both approaches. Now hopefully it gives us the same answer both ways. If not, we've either made a mistake or there's a problem with one of these formulas, which there isn't. So let's find out the pressure at 2, both approaches. I'm going to pause, give you a moment to solve it out in your notes there, then I'll show you on the whiteboard what it's supposed to be. Okay, the full version of the hydrostatic equation is P1 divided by gamma plus Z1 is equal to P2 divided by gamma plus Z2. So what this is saying is that if you go up in elevation, you're going to have a decrease in pressure. But if you go down in elevation, you're going to have an increase in pressure. Between 2 points, those things are conserved. So between location 1 and location 2, the sum of these two terms will remain constant. So we know both the elevation and pressure at 1. We know the elevation at 2. Our unknown is the pressure at 2. So I can rearrange that hydrostatic equation to solve for P2. It's going to be P2 is gamma times P1 divided by gamma plus Z1 minus Z2. Now, by the way, the problem statement never said what the unit weight of water is. That's a fluid property that I hope that you'll memorize. Both the density of water, the unit weight of water, and probably even without any effort of memorizing it, you're just going to eventually learn certain constants through the semester, and that's one of them you kind of just need to know. So if we substitute in the values for this, the pressure at 2 is going to be 9810 newtons per meter cubed times the pressure at the pressure at 1. Now if we're doing this in gauge, and then we'll convert to absolute at the end, so that is 0 plus Z1, so 50 meters minus 15 meters. So that pressure is 343,350 newtons per meter squared, and that's the gauge pressure. So it asks to find it in both gauge and absolute. So P2 in absolute terms is going to be this gauge pressure plus 101,325. So 343,350 pascals plus 101,325 pascals. So the gauge pressure at 2 should be 444,675 pascals, absolute. Okay, so that's the pressure at 2 if we use the full version of the hydrostatic equation. If we do the abbreviated version of the hydrostatic equation, then what we're saying is delta P is delta H times gamma. Okay, so the change in pressure is going to be 35 meters multiplied by the unit weight of water, 9810 newtons per meter cubed. So the change in pressure is going to be 343,350 newtons per meter squared, which is the same thing as a pascal. So that's our gauge pressure, because at 1, the pressure was 0. So it starts at 0 and it increases by 343,350. And so the pressure absolute will be this same pressure plus 101,325, which is atmospheric on the absolute scale. So it'll be 444,675 pascals, plus 101,325 newtons per meter squared. So our absolute pressure is the same regardless of whether we use the full version of the hydrostatic equation or the abbreviated version of the hydrostatic equation. Any questions about that example? Yeah.
Z1 and Z2 measure from the bottom?
Yeah, I was saying let's assume that the bottom of the tank is our datum, but we could have used the top of the tank as our datum and we'd get the same answer as long as we measure both points relative to that datum. We could have said let Z1 be 0 and Z2 be negative 35, and it still would have worked out. Other questions about this example? All right. Now, the hydrostatic equation describes conditions as long as the water isn't moving. So let's consider just a little illustration. I don't think this is in your notes. This is another bonus. Let's say that we had a reservoir and a water fountain was directly connected to that reservoir. It's not really like this. In reality, there'd be a treatment plant in between so that you don't have to drink dirty water. But let's just assume we punched into a dam and we've got a water fountain at the other end of that dam. So in an example like this, we know the water surface elevation. Sometimes in problem statements that'll be abbreviated WSE, water surface elevation. So we know the water surface elevation and we know where the fountain is, the elevation of that fountain. So let's go through and calculate what's the pressure in the water fountain and then compare that to the manufacturer says that the maximum pressure at the fountain can handle is 850. So if we were going to take that pressure all the way up to the limit, how high could the water elevation go in order to keep the pressure inside the fountain no greater than 850 kilopascals? And then question C is kind of just more of a thought question. We'll talk about that. But first, what I'd like you to calculate is the pressure in the fountain and then the maximum allowable water surface elevation. And probably the easiest way to do this one, of course, since you've got the elevations, you've got Z1, you've got Z2, you might as well use the full version of the hydrostatic equation. Or you can calculate delta H by finding the difference of those two elevations. Feel free to collaborate and talk amongst yourselves. In just a minute or two, we'll go over the solution together. All right, so when we find the pressure in the fountain, we assume that the air pressure, the pressure of the air that's just immediately in contact with the water, we're using that as our baseline. So we're saying air pressure is 0. We want to know the pressure in the fountain over and above the pressure of the surrounding air. So that means we can apply the hydrostatic equation and assuming that the air pressure is 0. So let's zoom in on this a little bit better there. All right, so we've got the elevation of the water, the elevation of the fountain. I calculated the delta H based on the two elevations that were given, based on the water surface elevation, the difference between that and the fountain. So it looks like 27 meters of water is going to give us 265,949 pascals, so about 266 kilopascals. Ironically, that's just like the bare minimum pressure that most people would consider acceptable. So you need about a column of 27 meters of water to generate enough pressure that people are going to say, yeah, that's enough to flush the toilet and have a good shower. So that's kind of at the bottom end of the spectrum for typical municipal water pressures. On the other end of the spectrum, 850 is usually used as a maximum design pressure for municipal networks, and often the limiting factor are water fountains and hot water heaters. They sometimes will have like pressure seals that are a little bit sensitive to anything greater than 850. So they could start to leak beyond that. So if we're saying the maximum pressure is 850, then what we're solving for is how high the water can be above the fountain. So we're solving for a delta H there. So we could have 86 meters of water above the fountain. And so if we know the fountain elevation is 588.36, then we go 86 meters above that. So that works out to a maximum elevation of 675 meters. So anybody else get that same elevation? That would be our maximum. We wouldn't want the lake to go any higher than that because then our water fountain might leak. All right? So we'd have to tell whoever's operating that lake not to let the water elevation get too high. Now what about this third one here? What effect would a longer pipe have on the static pressure? Okay, you're right, none. Why? It's only the heights, the same elevation. Now the key here is what we've been using so far is called the hydrostatic equation. it only describes pressures accurately if the water isn't moving. So if we had water flowing through the pipe, then there would be energy loss due to pipe friction. And we wouldn't be able to use the hydrostatic equation to correctly describe what's the pressure at the end of this pipe. But if conditions are static, then pressure only depends on vertical distance. And it looks like this is a horizontal pipe. So if it's static conditions, meaning that there's no velocity, no flow rate, then the only thing that dictates the pressure in this fountain is the vertical height of water above it. So it doesn't matter what the diameter of the pipe is. It doesn't matter what the length of the pipe is. It doesn't even matter how rough the pipe is, whether it's a really smooth, polished glass versus a really rough cast iron. It all have the same effect when conditions are static. So that's a little thing to file away in the back of your mind, is that this equation really isn't useful for conditions where the water is flowing. But there are plenty of situations where it is useful. So we'll continue to use it for now. Any questions on this example? All right. Let's talk about pressure transmission. Maybe you've been to a garage before where they have a hydraulic lift. I sure wish I had a hydraulic lift. Anytime I want to change the oil, I got to lay down in the dirt and shimmy, you know, like kind of like using your shoulders to shake under there. And I drive a Miata. That thing is like 4 inches off the ground. So I really, really have to squeeze when I want to change the oil. It's miserable. So the idea of a hydraulic lift, that would be so beautiful, is you could just get it up and makes the job so much easier. But we're not here to talk about that. What we're talking about is how the pressure that's produced in one part can be transmitted into a force in another part of the system. So not shown on this drawing is there's a compressor someplace. And what the compressor is doing is it's taking the air from outside the compressor and it's shoving it in to the headspace above the oil. And then what this is happening is the air is pushing down on the oil, and so now there's a lot more pressure inside the oil than there would be if it was just open to the atmosphere. And if it was open to the atmosphere, then the pressure acting down on the oil would just be 101,325 pascals. It would be our standard pressure. But we can increase that pressure, and what it does is the pressure is inside that interface of the oil and the air, and then the pressure increases a little bit as we go down through the oil, and then when we go sideways, what happens to the pressure there? Nothing. When we go up, the pressure decreases a little bit, and now we've got a pressure at this interface of the oil and the cylinder. And what happens is that the pressure is acting up on that boundary, so the pressure is pushing up. And because we had the compressor running, it's a pretty high pressure. And we can generate force. Force is a pressure acting over an area. And so here you can notice in the sketch they've given us the diameter of that. It's probably made out of steel, some sort of like a steel support with a 25 centimeter diameter. That allows us to calculate the area. And if we know the pressure inside of this system, then that would tell us how much force we're able to lift. So let's just put some specific numbers into play here. Let's say, what if this compressor is able to take the air pressure up to 600 kilonewtons per square meter. And we know the diameter of the tube there. So what is the force lifting up the car? Okay, so I'll do that on the whiteboard here. All right, so essentially what we're going to assume is that this vessel is connected to a tube that goes over here and here's that interface. It's the steel. All right. And the air is above it, and the air is acting down with the pressure of 600,000 newtons per meter squared. And so that's the same pressure that is going to be acting on that steel face. So the pressure acting on that steel face is 600,000 newtons per meter squared. And the area, we can calculate the area based on the diameter that's given. It said that the diameter in the example is for 25 centimeters. And so area is pi d squared divided by 4. And so pi, our diameter is 0.25 meters squared divided by 4. I guess in the slide itself I told you that that area is 0.04909 meters squared. All right, so in the example, area is that. So force is pressure times area. Okay, so 600,000 newtons per meter squared multiplied by the area of 0.04909 meters squared. So it can lift up 29,454 newtons. And how much is that in terms of mass? Well, if we know that mass is the weight divided by g, then that's about 3,000 kilograms of mass. So that's a really heavy car. That's like a Mercedes heavy, all right? 3,000 kilograms, that's more than 6,000 pounds. All right, so now consider these other questions that are posed here. So the force that's lifting up the car is 29,454 newtons. And that's just with things in the equilibrium that they are now. But what if we disturb the equilibrium? What if we turn on the compressor? Like it was like this when it was 600,000 pascals. But what if we turn on the compressor and we put some more air into the headspace above the oil? What's going to happen? What's that? Well, but the weight of the car hasn't changed. So let's say that it's the same car that it always was, but we turn on the compressor some more. Then what happens? It's going to go up. But what is it going to go up forever? Let's say that we turn on the compressor, and instead of 600,000, what if we turn it up to 602,000 newtons per meter squared? So we just add a little bit more pressure. Well, what's going to happen is it's going to lift it up, and then it's going to stop. It'll come into a new equilibrium. And so if we add more pressure, then it will go up higher, and then it'll stop. And it will go up. There will be some delta H. And so we could find out the delta H based on, like, I guess this is some sort of an oil. We could find out how much higher it's going to go, because delta H is going to be delta P. Delta P is delta H times gamma. So if we rearrange that, it's going to be delta P divided by gamma. So we could find out how much extra pressure we put in. We could find the unit weight of the oil, and then that would tell us if we add a little bit more pressure with the compressor, how much higher it would lift that car. So it would just be another application of the hydrostatic equation.
Would the left side go down?
Yeah, it would. Because in order for it to lift it up, it would need to be using some of that oil. There might be some sort of like a reservoir of oil that always can pump it in, and so that don't run out. But if it was a sealed system, then yes, for this to go up, the oil on the left would have to go down. So it would be the net difference between the oil on the left going down and the oil on the right going up, would be the delta H that we'd measure. Does everybody understand that? It would come into equilibrium again. So equilibrium means that things are moving and then they stop moving, like the system is in balance. That's equilibrium. And so the hydrostatic equation would be valid once it stopped moving. Once it was in equilibrium again, then we could say, all right, that deflection delta H and the delta P are related. Now what about this? Right now, this whole example has been illustrated with a 25 centimeter diameter cylinder. What would be our lifting capacity? What would be the change in the lifting capacity if we doubled the diameter? Look at the formula. The formula that we're using here is force is pressure times area. So let's say our capacitor, the compressor is the same. So maybe the best our compressor could do was 600,000. We can't get a bigger compressor, but maybe we could make the area larger. So that would allow us to lift more force, because if we have more area, that gives you more force. And so if you look at the formula for area, if you double the diameter, you're going to have 4 times as much area. So you could lift 4 times as much force by doubling the diameter of this cylinder from 25 centimeters to 50 centimeters. Yeah?
With the same amount of, with the 600,000 pascals in a bigger diameter,
yep.
It wouldn't go up as far with that same amount.
So now you're talking about if we turned it back on and it was moving?
I was just saying if the same amount of pressure is applied, but the diameter is bigger, it wouldn't go up as far, right? Or is that wrong?
Well, it's true, like this part where I said what happens if we turn the air compressor on. So now it wouldn't lift as much for increases of pressure. But if all we did was not turn the air compressor on, let's just say we could instantaneously switch out the 25 for a 50, then what that means is that instead of lifting up about 3,000 kilograms, we'd be able to lift up 4 times that amount. But you're right, when the diameter increases, then the volume of liquid that's going to be displaced is less. So pressure transmission. Here's an example that is walked through in your text, and I'm not 100% satisfied with the way that example is illustrated, so I thought I'd break it down and we go through the steps together, because it's not always obvious where the forces are and how it's turning it into pressures and so on. So this is a jack that maybe you'd be able to use for lifting up a vehicle, and it's using both mechanical advantage and also pressure transmission to support a load. So what happens is the user applies a force here at the handle, and then it allows you to lift something that is much greater than the force that's applied at the handle. And so what this example is saying, what if we push down on the handle 100 newtons, then what force would the jack be able to lift if we did that? All right, so let me sketch a couple of the components here. We've got the handle, all right, and the handle, the force is applied in the center of the handle. We've got this little pin at C, but then the force that is going to be acting up on the handle is at B. And so I'm not on the handle, but on the bar. So if we push down on the handle, then there's going to be a force acting upward at B. And what we need to do is a moment analysis about that handle. So let me switch this off. Okay. So the dimensions here is that it's 30 centimeters from the point of the reaction to where we apply the force, and then 3 centimeters from that, I'm going to call it F sub B. That's the force that's coming up at location B. So it's 3 centimeters from location C to that spot. And so if we do a moment analysis about C, then it's 100 newtons is the force that's applied at the handle. And that's going to be causing this whole system to rotate counterclockwise. So we've got 100 newtons acting at a total distance from C of 33 centimeters. And when it's in equilibrium, there's going to be some force at B resisting that so that it's not rotating. But the moment distance is only 3 centimeters. So this is the mechanical advantage part of how this jack works. It's using, like I said before, both mechanical advantage and also pressure transmission. The first part of it is the force at B is going to be 1,100 newtons. And that's significant because it is that force that's acting in a little plunger device. And so it's causing the pressure inside the jack. There's going to be 1,100 newtons acting down over some area that I'm going to call area 1. And so, basically there's this reservoir of fluid inside the jack. And here's this plunger. It's going down, and it's pressurizing all of the liquid because of the force that's applied. And remember, in the last example, we saw that force is pressure times area, and what we had was a known pressure and a known area. We calculated the force. We're going to rearrange that for this because we don't know what's the pressure inside that liquid. All we know is how hard we were pushing, and therefore, what is the force at that reaction point. So that's the force that's acting up on the bar. That's also the force that's acting down on this plunger. And so we can find out the pressure in the liquid. The pressure in the liquid is going to be that force over the area that it's applied. And so the force, again, was 1,100 newtons. And the area that it's applied over is related to the size here. So I think in the example it says it's 1.5 centimeter diameter. This area 1 is pi d squared. So the diameter of 1.5 centimeter is going to be 0.015 meters squared divided by 4. So that is 0.0001773 meters squared. Any questions so far about what's going on? Basically what we're just trying to do is we're trying to find out what is the pressure of the liquid inside that jack. Something's causing it to pressurize. In this case, it's our hand pushing down on the handle, which causes that plunger to go down with even more force because of the mechanical advantage. And the area over which it acts, 0.0001773 meters squared, means that the pressure inside that jack is 6,225,000 newtons per meter squared. So it's 6.225 megapascals. All right, now the other part of the problem is related to a difference in areas. So it's a larger diameter over here on the right side. And so this is our A2. On the other side of the jack, the cylinder that's acting upwards has a diameter of 5 centimeters. And so A2 is going to be pi d squared divided by 4. So the diameter is 0.05 meters. We square that, multiply it by pi, divided by 4. That's 0.0019625 meters squared. So we have essentially pressure that's acting upward on some area. The pressure, we remember, is 6,225,000 newtons per meter squared. We know the area, that A2 area. So the force is pressure times area. So 6,225,000 newtons per meter squared. And the area is 0.0019635 square meters. So the force is 12,222 newtons. That's the force that's applied at location 2. That's the load this jack can lift. So if A1 and A2 were the same, like if the two diameters were equal, like this plunger and the other one, if they were the same, then it would only be able to lift 1,100 newtons because that was the force that was applied from B. But it magnifies its lifting capacity by having the same pressure act over a bigger area. And that was an idea that took a long time for me to wrap my head around. Like, I remember the first semester I taught fluid mechanics. It was in 2005. So think about where you were in 2005. I was teaching fluid mechanics for the first time. And I sat there in my office thinking, I was like, but it seems like it's creating energy. You know, like thermodynamics says energy can't be created or destroyed. I was thinking, this just seems wrong somehow, that you could lift increasingly larger amounts by having a larger area that it acts over. But that's exactly how it works. I just needed to adjust my thinking to adapt to that new reality that, you know, that's pressure transmission. If it acts over a larger area, you can lift heavier things. So are there any questions about this example or the calculations that I did on the whiteboard? All right, let's talk about a way to measure pressure. There's something called a piezometer, and a piezometer is a very simple way of measuring the pressure inside of a pipe. If you have a pipe, and let's say that it's carrying a liquid rather than a gas. So if it's carrying a liquid, one way to measure the pressure is to cut a hole in the pipe and then connect a tube to that hole. And the water level will rise to some elevation, and then it will stop when it comes into equilibrium. Like if we punched a hole in the pipe and there was no tube there, then just the liquid would be spraying all over the place. But we've put enough of a sleeve around that hole so that the water can rise upward, and then it comes into equilibrium. So this H is closely related to the pressure inside of the pipe. So if the H, the water level, rises to a distance of 10 meters, then all we have to do to find out the pressure in the pipe is apply the hydrostatic equation. Okay, so to apply the hydrostatic equation, remember that delta P is delta H times gamma. So delta H is delta P divided by gamma. So in this case, the pressure in the pipe is going to be the 10 meters, and if it's water that's in there, then we'd use 9810 newtons per meter cubed. So that tells us the pressure in the pipe is 98,100 newtons per meter squared.
Is that 10 meters from the center of the pipe or from?
Yeah, it's from the center of the pipe. Good question. Normally, the pipe diameter is going to be relatively small relative to the delta H. You know, like a typical water pipe for under the roads would maybe, like a big one would be 12-inch diameter. That would be a big water pipe. And so you're talking about maybe 25 or a really a small fraction of the H. But it's customary to measure from the center of the pipe. So if we rearrange the hydrostatic equation for delta H, then that tells you how tall the piezometer would need to be for a certain pressure. Do you remember what I said was the maximum pressure that you might see in a municipal network? We talked about any more than that, and the water heater may start to leak, or a water fountain fitting might start to leak. 850 kilopascals. So let's find out how big of an H would you need if you're going to have a municipal water network. If you're going to have 850,000 newtons per meter squared, and water typically is 9810 newtons per meter cubed, what's the delta H that goes along with that? Anybody have a calculator handy and tell us? 86.64 meters. Now that's a problem. What it tells us is that a piezometer is not really an effective way of measuring water pressure for like a city pipe network. Imagine if this was the only way that we had to tell what's the pressure in a pipe, then we'd have to have these piezometers coming out of the ground, and the water level would be 86 meters, potentially as high as 86 meters above the pipe. So you'd have to have really tall stilts, or maybe like a jetpack, to get up there and see like where the water elevation is. All right. So the point is that piezometers are impractical for high liquid pressures, and for gas pressures they're useless because the gas would just escape out of the opening. So we will actually use piezometers for a couple of experiments through the semester, but we'll move on to more sophisticated ways of measuring pressure. This is the most basic of them.
Is surface tension not factor into it at all?
It depends on the diameter of the tube and what the tube is made of. That's a great question. In this case, we're assuming that the diameter of the tube is big enough that the surface tension would be negligible. But if it was a really small diameter tube, remember, the smaller the diameter of the tube, and especially if it's made out of glass, then the water level may rise up due to the capillary effect.
Why would you measure the pressure like in some length into the pipe as opposed to like the source of where the fluid's like coming from?
So you're saying if we had a water treatment plant, yeah. So like here's, oh geez, this thing. Throw this one away. If we've got a reservoir of some sort and it's going over here to a building, so you're asking like why would we measure here if we maybe already know the elevation here? There's a variety of reasons. Like if you have a sudden decrease in pressure at a certain location, that might tell you that there's a pipe break, and so we want to know in lots of spots in the network what the pressure is, because the pressure at that location can tell you the flow rate through the pipe. It's an indicator of where demand might be. So if you had a normal pressure reading at this spot, but then a really low pressure reading at another, then that would tell you potentially that there's a break in the pipe. That's just one example of why it'd be interesting to know the pressure. It might also be that we have booster pumps at different locations. And so if you've got a booster pump, that'll only turn on if the pressure is low. And pressure decreases when there's lots of flow through a pipe. So we may want to know the pressure at different spots to tell us where to turn on these booster pumps. Other questions about manometers? All right, let's talk about some of the key ideas in the homework that you've got coming up. I think this is one of them, 315. Let's just make sure here. Yeah, 315. All right, so we'll go through a couple of these. Because there's so many of them, I kind of want to help you get started breaking it down. So what it says is that the air space pressure is 50 kilopascals vacuum, and the water height rises to H if the airspace pressure is changed to 25 kilopascals vacuum. Will H decrease or increase, and by how much? All right, so let me help you visualize what's going on. If we talk about absolute pressure, the atmosphere's absolute pressure in this one, under the circumstances that are described, the pressure at the interface of the gas and the water is 100 kilopascals absolute. Now, if you go down, the pressure is increasing. If you go up, the pressure is decreasing. So what this is saying is that initially, there's 50 kilopascals vacuum. So that means less than atmospheric. So that would make this 50 kilopascals absolute. So it's just saying less than atmospheric. So you can calculate the delta H with the hydrostatic equation. Oh, another dead one. I've got the golden touch today. I think I've got one more in reserve. All right, so the hydrostatic equation is what you can apply there. And the delta P is going from 100, because the air and the water have 100 here. And if you extend that line into the tube, it's going to be the same. Because we have static conditions. We can go down, over, and back up inside the tube. The pressure here is equal to the pressure of the atmosphere. But then as you continue to move upward through that glass tube, the pressure continues to decrease until you get to the air. And it's assumed that everywhere inside here, the air is the same. Because gases have such a low specific weight, in a problem like this, I mean, if you go up through the atmosphere hundreds and hundreds of meters, there's a decrease in pressure. But in a little device like this, all of the air has the same pressure. All right. So find the H before, where the vacuum was 50 kilopascals. Find the H after, and they're asking by how much does it change. So that just means find the difference between the two. All right. You guys have these key ideas in your handouts, right? It's included in the notes? All right. All right, so this one, there's a weight that's acting over a piston. So you see that the diameter of that is specified. So you're going to assume a circular shape, calculate the area, and you've got a weight acting over that area. The question is, how high is the liquid level going to rise if it's open to the atmosphere here? So again, this is just combining the two ideas together that we've been talking about today, pressure transmission and the hydrostatic equation. What pressurizes the liquid is a force acting over an area. So force is pressure times area. So pressure is force divided by area. And the force that we're talking about is the 5 kilogram weight. So you'll have to use weight is mass times g, because they've just given you the mass and you're going to need to know the weight. You can calculate the pressure inside the liquid, and then the thing to remember is that the pressure at that interface between the piston and the oil is the same as the pressure over here inside this right leg of the tube. And that's why they're giving you this dimensions of H2. H2 goes from the interface of the oil and the piston up to the interface of the oil and the atmosphere. So it's just a simple hydrostatic equation problem once you find out the pressure inside the liquid. Why do they give you the unit weight? Why, or actually they don't give you the unit weight. Why do they give you the specific gravity? Right. It's to calculate this gamma you're going to need for the hydrostatic equation. Remember, the definition Sg can either mean the density of something relative to the density of water, or it can also mean the unit weight of something relative to the unit weight of water. And so you just always, when you're applying the specific gravity formula, you assume that the unit weight that it's talking about is 9810 newtons per meter cubed, and then you multiply it by the Sg that's provided. Any questions about this problem? All right, this one's a little tricky. All right, so what's hard about this one is to think that you've got water in some weird looking like dome structure, and it's a hemisphere. It's basically, there's a tube connected to a hemisphere, and so this is water all the way up inside the tube and also down inside of the dome. And they tell you that L, this dimension L, is 80 centimeters. And so because you know the total distance from the water all the way down to the bottom, you can find the pressure all the way down there. And if we were to look from above at what we're seeing here, it would be circular, and then here's that little opening. Okay, so we're looking down on something that's circular, and so there is an area, a cross-sectional area, that all of that water is pushing on. And remember that force is pressure times area. So you use the hydrostatic equation to find what's the pressure at the very bottom of that system. And we say that we can do a force balance in the vertical direction. And there's going to be equilibrium. If those bolts weren't pulling the system down, like if these bolts weren't strapping this dome to whatever the ground is, then the water would be leaking out. That would be the tendency, is that there would be so much pressure at the bottom there that the water would be forcing its way out underneath the dome. So that's why those bolts are there. The bolts are pulling the system down because effectively the pressure, the water is pushing down on the ground, but the ground is also pushing up on the dome because of the water pressure. So here is all of the forces in the vertical direction. You've got the pressure of this bottom surface. Like let's say this system, if it's strapped into concrete, the concrete is going to be pushing upward to resist the weight of the water. The weight of the water is downward, the dome is downward, and then the bolts are also pulling down. So if you look at this, it's saying what is the force from the bolts required to hold the dome in place? Well, everything is going to be known here except for the force of the bolts, because they tell you the weight of the dome and the pipe is 6 kilonewtons. You can calculate the weight of the water by calculating the volume of the water inside of this hemisphere. And I think in the back of the book it gives you the volume of a hemisphere, the equation for that. You may need to look it up in terms of radius. Some comes to mind, 4/3 pi r cubed, something like that. You'll find the equation in the appendix, but take note of this is a hemisphere. So it's not a total sphere, it's half of a sphere. So you're going to need to know the volume of water in here and also the volume of water inside that cylinder that sticks up. So the weight of the dome is given, the weight of the water you calculate, the pressure you're going to calculate based on the hydrostatic equation and the area of that bottom area that the pressure is acting over, and it's acting in an upward direction because it's resisting the weight and the pressure of the force that's down. So then the only thing left to bring it into equilibrium is the bolts. So this one's a little bit tricky to kind of like mentally visualize, but if you start crunching the numbers and have any questions, just feel free and let me know. That's it for today. Let's take one last look at these announcements before we finish a couple of minutes early. So again, I really encourage you to make good use of the feedback the grader has given you and get an early start on this homework assignment while those key ideas are still fresh in your mind. All right, I'll see you Thursday.